Hello, class. So on this video, we'll continue on section 3.7. Right? In the previous video, we finally worked through an example where I gave you a situation like the one in the setup that we have, right? So a spring mass system in which we have no damping and free vibrations and simple harmonic motion, which we always assume. Right? And then we worked through the word problem, right? So I gave us all the information. We saw that the hard part was really just to get all the units right? All the units to match. Once all the units match, so it was a little bit of analysis to find the proportionality constant K, right? But just use the fact that at the equilibrium state, the magnitude of the restoration force has to be equal to the weight, right? And that's what we did in this part here, right? To solve for K. Right? To solve for the mass, right? All you need is the weight and the acceleration due to gravity, right? Because weight is by definition the acceleration due to gravity times the mass, right? So you have the acceleration due to gravity and the weight, let's divide, like we did here, and you get the mass. Right? Again, the hard part is only showing that the finding or making sure that the units match. Once you have that, you can just plug everything into our differential equation, right? And then, of course, deal with the initial conditions. Okay? But all that work is easy, right? The hard part is really just trying to make sure all the units match. Now, as I mentioned, I'm going to give you a formula so you can change a, oh, wait. I should have been, I don't know why I'm writing Y. Should have been writing X, because I'm using X for the variable. So I guess there's no place. Yeah, I am using X. Okay, sorry. This should be X. This is X of T. Yeah, I forgot. So see, I'm also used to just working with Y's for the dependent variable. But it's good to do this because, actually, let's call it X sub C. This is the complementary solution. It's good to do this because, again, the names of the variables shouldn't matter. It's just what they are. Okay, so now I'm going to show you a formula as we saw in the previous example, and I've mentioned before. It's not obvious that this solution is a sum. It's just one single sine or one single cosine. But there is a simple formula to write it in that way. So given a solution, which I'm assuming that you found, so X of T equals C1 cosine of omega T plus C2 sine of omega T, you can always rewrite it. I'm not going to prove it. It's just doing some trigonometry, right triangle trigonometry, as X of T equals A times sine of WT plus phi, so this new angle phi, where I give you what everything is. A equals the square root of C1 squared plus C2 squared. So the coefficients that you found here. In our particular example, it would be 0.203 and 0.406. And then phi satisfies the tangent of phi equals C1 over C2. Right? So you can take tangent inverse, right, to find what phi is. Right? So if you want to write it as sine, you can do it like that. If you want to write it as cosine, it's the same thing. You just change the inside where it's plus phi by minus phi, and you change the ratio of tangent of phi to tangent of phi equals C2 over C1. Right? And that's it. Right? You have all the parts. You have W, you have C1, you have C2. Right? So all you have to do is find A, which I give you the formula, and phi, which I give you the formula. Now, one reason why it's useful to write things like this is, well, you can see the period immediately. Not only that, you can also see the amplitude. Right? The amplitude is by definition the distance of the equilibrium point to the highest mountain, to the peak of the highest mountain, or the bottom of the lowest valley. So whatever distance that is, that's the amplitude. So it's something that's useful to know, right? In a lot of applications, what the amplitude is. Again, amplitude is related to sound frequency, so it's good to know, or radio frequency. Okay. So in terms of examples, I'm not going to do any example of this because you can just plug things into the formula. And if you ever need the formula, you can just look back here. Right? What's important is that you know how to derive this solution. This is a solution that matters to me. If we can do this, we can do the other part because it's just plugging things into a formula. Okay. Just wanted to make a note of that. I did promise I was going to give you that, so I give it to you there. Now, let's say we want to generalize our setup. Now we want to introduce some damping. Okay. Remember, damping are forces that are going to make our system lose energy. Okay. So, as usual for us, this damping force is going to be proportional to something. So in mechanics, it is usually assumed that the damping forces acting on a body are proportional to a power of the instantaneous velocity. In particular, they're proportional to a power of the derivative. We don't know exactly what power it's proportional to, but for this class, we're going to assume that it's proportional to the first derivative, to the power of the first derivative. So again, in general, it could be a second power, a third power, so it could be the derivative squared, the derivative cubed. In this case, we're just going to assume that it's proportional to the derivative itself, right? So the first power. Right? Now, if we do that, so going back to Newton's second, to Newton's second law, and the fact that the total force is sum of the forces, right? We got this from the previous, right? This is from when we had no damping. So now we add a damping force here, which is going to be proportional, right, to the derivative, the instantaneous velocity. So I'm going to write it as beta times dx dt. And I actually should change beta, right, for something else, because beta we use for complex numbers. But for now, let me just leave it as beta. No, let's yeah. For now, let's leave it as beta, where beta is greater than 0. So here I'm telling you that beta is going to be greater than 0 because it's not as easy to determine what beta is, right? So we don't have this Hooke's law to determine exactly what's going on, right? So I'm just going to tell you beta is bigger than 0. Now we add the force as a negative, right? Because it's acting in the direction opposite to motion, right? So that's why I put it as a negative instead of a plus. But other than that, I'm just adding the force. So the force, the total force is sum of its forces. And my Newton's second law, we know that's equal to mass times acceleration, which is the second derivative of x with respect to time, right? So really, don't worry too much about why we know that the damping forces are proportional to a power of the derivative, or why we assume that it's the first power, or why beta is greater than 0. Don't worry about any of that for right now. Just all of that is given, so all you have to focus on is this differential equation. Okay. Now, as before, we're going to rewrite this differential equation. Okay, so I'm going to move everything to one side, and then I'm going to rewrite some things. Right? So as before, I'm going to call w squared just k over m, and beta over m. Right? And you can see that when you simplify this, you add everything to the other side, divide everything by m. So you have beta over m times dx dt. That beta over m, I'm going to write it as 2 times lambda. Okay, so this is the Greek letter lambda. So that my ODE looks like this. Now, the reason why I do this is because then when I find the characteristic polynomial, it simplifies the roots to this easy form. And again, you don't have to do any of this, right? Because all of the coefficients are constants. You can just find the characteristic polynomial using the actual names, right? So instead of 2 lambda, you can use this beta over m. Instead of w squared, you can use this k over m and find the characteristic polynomial, and you're going to get the same roots. It's just that giving them these names makes this equation for r just look nicer. Okay? That's the only reason why I do this. Okay? So again, these are the roots of the characteristic polynomial. It's given by r equals this. And as we know, we always have 3 cases, right? These roots could be real distinct, 1 real with multiplicity 2, or 2 distinct complex roots. And if you remember, when I was doing that analysis, it all depended on what the inside of the square root was. If the inside of the square root, which for us ends up being after we simplify everything, and that would be a good exercise, but showing that under these definitions, so 2 lambda equals beta over m, and w squared equals k over m, you actually get this form for the roots, right? So so as I was saying, what matters is what's inside the square root. If what's inside the square root, which in this case is lambda squared minus w squared, if that's greater than 0, we get 2 distinct real roots. If it's equal to 0, we get 1 root of multiplicity 2. And if it's less than 0, then we're taking the square root of a negative number, right? So then we get 2 complex roots. So really what's determining what's going on is this relationship between lambda squared and omega squared. And just so it's clear what these things are, you can just solve for lambda, right? So since 2 lambda equals beta over m, then lambda is beta over 2m. So lambda squared is equal to beta squared over 4m squared. Right? If you want to think of it in terms of beta and m, right? And w squared, we know what it is. It's k over m. So really, what determines whether we have two distinct roots that are real, two distinct roots that are complex, or just one real root multiplicity 2 is the relationship between these two quantities, lambda squared and w squared. Now, let's see what's going on in each of the cases. First, the case where lambda squared minus w squared is greater than 0. As I mentioned, this is the case where we have, or as we know, this is the case where we have two distinct real roots. In terms of the language of this system, we would say that the system is overdamped. Okay, so in terms of what we learned before, this is the case where we have two distinct real roots. In terms of the language of this system, it's saying that the system is overdamped. In terms of when is it the case that lambda squared minus w squared is greater than 0, that happens precisely when beta squared over 4m is greater than k. And in this case, we know what the solution looks like, but we get two real distinct roots, right? So we know that the solution is just a linear combination of exponentials. There's no cosines or sines, right? Meaning that we don't get any oscillatory motion in this particular case. So that's the first case. Two real distinct roots. It's the same as saying that the system is overdamped. It's the same as saying that there's no oscillatory motion. Right? Or equivalently, beta squared over 4m is greater than k. If you want to work with beta and m and k instead of lambda and w. The second case, where lambda squared minus w squared equals 0. Again, we know that this corresponds to the case where we have one real root of multiplicity 2. Okay. Now, in this case, in terms of the language of the spring mass system, we would say the system is critically damped. Okay. Why do we say it's critically damped? Because if we decrease beta just a little bit, the smallest quantity, it would cause the system to have oscillations. Okay. Why? Because in terms of beta, m and k, this is the condition that needs to hold, that beta squared over 4m equals k. The mass is fixed, right? K is fixed. The thing that's changing, that could potentially change here, is beta. Right? So beta right now, if this is true, that lambda squared minus w squared equals 0, beta satisfies this equation perfectly. Which means that if we reduce beta even a little bit, this quantity beta squared over 4m is going to be less than k. Meaning that lambda squared minus w squared is going to be less than 0, right? So that's why we say it's critically damped, because it's at this critical point where beta is perfect or exactly perfect that this equation is true, that lambda squared minus w squared equals 0. And if beta were even a little bit smaller, we wouldn't have, we would be back to the k square. Well, not back to, but in case 3, right? So what is case 3? Lambda squared minus w squared is less than 0. Again, this is what's inside the square root, so that means that we're going to get complex roots. In this case, the system is said to be underdamped. Right? Equivalently, in terms of k, beta, and m, k is greater than beta squared over 4m. And in this case, as we know, we get alpha and betas, right, because of the complex number. Oh, shoot, yeah. So this is where I should have changed the beta, right? Well, we get a complex number. The complex number has a part multiplying the imaginary part I. So we know that that thing goes inside the cosine and sine. So in this case, we get cosines and sines. So we do get oscillatory motion. So in terms of, so you can think of this either in terms of the roots, right? Whether we get two real distinct roots, one real root multiplicity 2, or two complex roots. But in terms of the system, you want to think of it as overdamped, critically damped, and underdamped systems. Okay. And again, because we know what the general solution is in this case, we know that the only case in which we get cosines and sines is case 3, where lambda squared minus w squared is less than 0. Or equivalently, k is greater than beta squared over 4m. Okay. Now, why are they given the names overdamped and underdamped? Well, what's happening in case 1 is that the damping force is too large. If the damping force is too large, right, or beta is too large, equivalently, and thinking of it in terms just of beta and k, then there's too much damping force and there's not enough force left over in the system or energy left in the system to have some sort of oscillatory motion. It basically just goes to 0 very fast. And you'll see that in the next example. However, if beta is not too big, and it's the case that k is greater than beta squared over 4m, then the damping force is not too large, meaning that we do get an oscillatory motion. So in this case, we get cosines and sines. And in terms of what's happening with the solution, it doesn't go to 0 very quick. So we actually get oscillatory motion. And as we know, we can write the solution in 3, and we can write it like this, as some amplitude times sine and cosine, which means that in the case that we're underdamped, so in case 3, we actually never go to 0. Why? Because there's eventually, so the solution is going to decrease and decrease and decrease, right? Because of the damping force, but eventually it's going to start oscillating between a and negative a, where a is the amplitude when you write it in this form. The solution, you write it in this form. So it's interesting how all of these variables relate and how the damping affects the form of the solution. Really, we only get oscillation in case 3. In all of the other cases, we get exponentials that go to 0. So it's interesting to see. Okay. So in the next video, I'm going to show you in Mathematica, I'm going to show you each of these cases, and I'll plot the solution, and you'll see how they look like.